February 14th, 1943. The sun blazed mercilessly over the Tunisian desert as German recovery crews worked frantically to extract their prize from the battlefield. Scattered around them lay the twisted wreckage of what had been a fierce armoured engagement, but their focus was entirely on one particular machine, an intact American Sherman tank, its white star still gleaming beneath hastily applied German crosses, sat waiting to be loaded onto a transport truck. This wasn't just another piece of captured equipment. This was intelligence gold that would soon trigger the most devastating realization in German military history. The tank bore the name War Daddy 2 painted in bold letters across its hull, serial number USA 3067641, manufactured by Lima Locomotive Works, formerly belonging to Company G of the 1st Armoured Regiment. What made this Sherman special wasn't its combat record or the circumstances of its capture. It was the simple fact that it worked. After days of cross-country movement through some of the harshest terrain on Earth, after surviving the chaos of battle, after being driven by German crews unfamiliar with its systems, this American machine just kept running. German tank crews watched in growing bewilderment as their new acquisition performed flawlessly during the 350-kilometre journey to the port of Sfax. No overheating, no transmission failures, no mechanical breakdowns of any kind. For soldiers accustomed to constant maintenance stops and frequent mechanical disasters with their own equipment, this level of reliability seemed almost supernatural. They had been told that American tanks were inferior products of a weak industrial nation focused more on quantity than quality. Yet here was proof to the contrary, humming along the desert roads with the kind of dependability German crews could only dream of. The order came down from the highest levels of German command. This tank must reach the testing facility at Kummersdorf intact and operational. Army weapons officials understood that they were dealing with something potentially revolutionary. Intelligence reports about American production capabilities had been filtering in for months, but seeing the physical evidence made those statistics real in ways that numbers on paper never could. This Sherman represented mass production engineering at a scale Germany couldn't match, built using automotive principles that German industry had somehow failed to master despite decades of technical expertise. As the ship carrying War Daddy 2 steamed northward across the Mediterranean, Wehrmacht engineers prepared testing protocols that would reveal uncomfortable truths about their own limitations and American capabilities. They had no idea they were about to witness the systematic demolition of everything they thought they knew about tank design philosophy. Spring arrived early at Kummersdorf Proving Ground, 25 kilometers south of Berlin. War Daddy 2 rolled off the transport rail car bearing its new German designation and license plate, already marked with precise measurements and technical notations. The facility served as Germany's premier testing centre for both domestic and captured Allied equipment, where meticulous engineers subjected every component to exhaustive examination. Here, teams of specialists would photograph every angle, measure every clearance, and document construction techniques that seemed impossibly straightforward compared to German methods. The transmission immediately caught the attention of powertrain specialists. Where German tanks employed straight-cut gears requiring precise tolerances and constant maintenance, the Sherman utilized herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design, standard in American automotive manufacturing since the 1930s, provided exceptional durability with minimal precision requirements. German engineers had dismissed such gears as too difficult to mass produce, given their industrial capabilities. The Americans had been manufacturing them by the thousands. Testing began with basic automotive trials designed to stress every mechanical system under controlled conditions. Engineers drove the Sherman through obstacle courses that replicated battlefield conditions, measuring fuel consumption, monitoring engine temperatures, and recording transmission behavior under varying loads. After each trial, They meticulously disassembled components to examine wear patterns and search for design weaknesses. The results contradicted everything German tank doctrine had accepted about the necessary trade-offs between performance and reliability. The Sherman performed adequately in every category and excelled in the one metric where German tanks consistently failed: operational endurance without maintenance intervention. This wasn't just, it was impressive engineering, fundamental philosophical difference that explained everything about American versus German approaches to armored warfare. The powertrain examination revealed design principles that prioritized practical functionality over theoretical optimization. The Sherman's transmission featured 5 forward speeds plus reverse, with synchronization in gears 2 through 5 that eliminated the need for double clutching during normal operations. This made the tank nearly as easy to drive as civilian automobiles, requiring minimal specialized training. German tankers, by contrast, spent considerable time mastering complex clutching techniques and careful throttle management to avoid damaging their transmissions. The Continental radial engine demonstrated remarkable tolerance for varied operating conditions that would have caused German engines to overheat or lose power. The cooling system, though simple in design, proved highly effective. The air filtration system handled desert sand without the frequent clogging that plagued German equipment in North Africa. Every system reflected a philosophy that accepted ordinary soldiers with basic automotive knowledge would operate these machines, while German designs assumed highly trained specialists would always be available. June brought a major armaments conference attended by Reich Minister Albert Speer and senior Wehrmacht officers. The demonstration program included hill-climbing trials comparing German and captured Allied tanks. War Daddy 2 sat alongside the latest German designs, including a fresh Panther medium tank and a Ferdinand tank destroyer, representing Germany's most advanced armoured fighting vehicle technology. Speer, personally accountable to Hitler for armaments production results, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration would provide answers neither Speer nor German tank designers wanted to acknowledge. The Sherman climbed the test slope smoothly, its synchronized manual transmission shifting without hesitation, while the engine maintained consistent power delivery throughout the ascent. The driver handled the vehicle with confidence that would become a Sherman hallmark. The Panther followed, its more powerful engine allowing it to match the Sherman's performance, but only barely and with considerably more difficulty. The Ferdinand, massively heavy and technically sophisticated with its electric transmission system, stalled partway up the incline. Speer watched as recovery crews struggled to restart the vehicle, an embarrassing failure occurring before dozens of senior officers and industrial leaders. The implications were becoming impossible to ignore. American tanks weren't just adequate competitors, they were fundamentally better engineered for sustained field operations than anything Germany was producing. The written assessment that appeared in Das Reich newspaper called the Sherman a praiseworthy product of North American steel industry, noting its fulfillment of the almost arrogant requirements of the North American automobile industry. These carefully worded statements, designed for propaganda purposes to avoid appearing defeatist, nevertheless concealed growing alarm spreading through German engineering departments. Back at Kummersdorf, systematic testing continued through summer and autumn. Engineers documented operational ranges exceeding 2,000 kilometers before requiring major maintenance, roughly 4 times what early Panthers could achieve in field conditions. They measured transmission efficiency that surpassed any German tank, with power losses through the drivetrain significantly lower than comparable German systems. The synchronized transmission made gear changes smooth and simple, requiring neither the double clutching nor careful rev matching that German transmissions demanded. The final drives presented another revelation that challenged fundamental German engineering assumptions about what was possible in tank design. German Panther tanks employed final drive systems inherited from Tiger design, a configuration that proved catastrophically inadequate under operational stress. The design used straight-cut gears in housings that simply couldn't handle the loads imposed by a 45-ton vehicle. Field reports from North Africa and the Eastern Front documented final drive breakdowns that left Panthers abandoned after movements of less than 100 kilometers. Crews learned to dread anything beyond short tactical movements, knowing their vehicles might not survive the journey to the battlefield. The Sherman's final drives, built using the same herringbone gear principles as the transmission, rarely failed even under sustained combat conditions that would destroy German components. Restoration projects decades later would discover Sherman final drives that required no mechanical work after years of storage, testament to design margins that exceeded requirements by substantial factors. This wasn't accidental over-engineering. It was deliberate American automotive philosophy applied to military hardware. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that painted a sobering picture for Wehrmacht technical branches. These documents, intended for senior officers and armaments ministry officials, documented American automotive engineering maturity that Germany fundamentally lacked despite its theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. The comparison became even more painful when field reports began arriving from combat units. Panthers required strict operational restrictions to prevent mechanical failures that would leave them stranded. Drivers received explicit instructions not to change gears frequently, as excessive shifting damaged the transmission. Third gear broke so often that field manuals warned against its use, except when absolutely necessary. Panthers couldn't turn while backing up, as this would destroy the transmission immediately. These problems existed despite Panthers being built in dedicated tank factories by skilled workers using the best materials Germany could provide. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford and Chrysler, applying mass production principles developed over decades of civilian vehicle manufacturing. The tank incorporated commercial automotive components wherever possible, leveraging existing supply chains and manufacturing expertise. Multiple manufacturers built transmissions to identical specifications with fully interchangeable parts that could be mixed freely without adjustment. This standardization, routine in American automotive industry, remained largely theoretical in German tank production. Additional captured Shermans arrived at Kummersdorf throughout 1943 and 1944, including tanks taken from British units in Italy and Soviet forces on the Eastern Front. Each vehicle underwent similar testing protocols, building a comprehensive database of American capabilities across different variants and production periods. The British had modified some Shermans with their 17-pounder anti-tank gun, creating the Firefly variant that addressed the Sherman's main weakness in firepower. German engineers examined these modified tanks with particular interest, noting how the Sherman's large turret ring accommodated the significantly larger gun with minimal modification. The Firefly demonstrated growth potential built into the original design that German engineers hadn't considered when specifying their vehicles. The Panther, rushed into production to counter Soviet tanks, had no capacity for significant armament upgrades without complete vehicle redesign. The automotive testing program expanded to include reliability trials specifically designed to replicate combat conditions. Engineers drove Shermans through hundreds of kilometers of cross-country movement, recording every mechanical incident and maintenance requirement. They compared these results with field reports from Panther and Tiger units operating on Eastern and Italian fronts. The numbers told an unambiguous story about comparative reliability that no amount of propaganda could obscure. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic rates as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 in 5 tanks were actually capable of combat operations. Sherman tanks maintained substantially higher operational availability across all theatres, a fact that German intelligence could no longer ignore or explain away. Specific data from German field reports documented Panther reliability problems in devastating detail. During Operation Citadel at Kursk in July 1943, Panthers achieved only 16% operational readiness, with mechanical failures eliminating more tanks than enemy action. By December 1943, readiness had improved to only 37%. The progression showed gradual improvement as design flaws were addressed, but even the best Panther readiness rates never matched what Shermans achieved from initial production. Engine lifespan told an equally troubling story. Sherman diesel variants exceeded 3,000 kilometers under proper maintenance, while Panther engines barely reached 1,000 kilometers even after improvements addressed the worst early problems. German reports from March 1944 documented improved Panther engines achieving service life of 700 to 1,000 kilometers, presented as a remarkable success. This improvement merely brought Panther engines to roughly 1/3 of Sherman diesel capability. Field reports from German units using captured Shermans reinforced the testing data with real-world operational experience. Mechanized units, desperate for reliable vehicles, eagerly employed any captured American tanks they could obtain intact. Unlike Soviet tanks, which Germans modified extensively before use, Shermans entered German service without changes. They didn't require modification because they worked correctly as designed, with no fundamental flaws needing correction. German tank crews who had experienced multiple mechanical failures in their own vehicles found the Sherman's reliability remarkable and frequently commented on it in correspondence. Reports from panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions before mechanical failure immobilized their vehicles. The psychological impact on German crews became increasingly apparent as the war progressed. Men who had been trained to believe in German technical superiority found themselves envying enemy equipment that simply worked when needed. The confidence that came from reliable machinery affected everything from tactical decision-making to strategic planning. American tank commanders could commit to operations knowing their vehicles would perform as expected, while German commanders had to calculate mechanical failure rates into every mission plan. January 1944 brought expanded testing programs as additional captured equipment reached Kummersdorf. Engineers examined variants with different engines, documenting characteristics and comparing performance across the Sherman family. Every variant demonstrated the same fundamental quality that German designs consistently lacked: excellent automotive reliability derived from sound engineering principles and quality manufacturing processes. The consistency across variants impressed German engineers who were accustomed to significant quality variations between different manufacturers producing nominally identical vehicles. Where German tank production suffered from inconsistent tolerances and manufacturing standards that made parts interchange problematic, American factories delivered remarkable uniformity. A transmission from General Motors could be installed in a Sherman built by Ford without adjustment. Components manufactured in Detroit worked seamlessly with assemblies produced in California. This level of standardization, taken for granted in American automotive industry, represented an achievement German manufacturing had never accomplished even in peacetime. The diesel-powered variant particularly impressed German engineers who examined it at Kummersdorf. Soviet forces had received thousands of these tanks through Lend-Lease, and significant numbers fell into German hands during retreats on the Eastern Front. The twin diesel engines provided performance matching any Sherman variant while consuming substantially less fuel than gasoline engines, a critical advantage as German fuel supplies dwindled throughout 1944. German designers had experimented with diesel tank engines, but abandoned the effort due to manufacturing difficulties and the complexity of fuel injection systems. American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules, demonstrating manufacturing flexibility and technological sophistication that German industry never achieved during wartime conditions. The implications were staggering. Americans were simultaneously mass-producing multiple engine variants while maintaining quality standards that exceeded German capabilities. March 1944 brought reports from General Heinz Guderian, Inspector General of Panzer Troops, noting in official communications that improvements to Panther reliability had achieved what he termed acceptable standards. Engine life had reached 700 to 1,000 kilometers, and final drive problems had been largely resolved through design modifications and improved manufacturing processes. This improvement presented a significant success in German military communications, merely brought Panther reliability to levels Sherman had achieved from initial production in 1942. The German army celebrated reaching standards that American tanks had exceeded from the beginning, highlighting how far behind German armoured vehicle development had fallen. Every milestone German engineers achieved had already been surpassed by American mass production months or years earlier. The technological gap wasn't closing, it was widening as American industry continuously refined and improved its processes, while German manufacturing struggled with increasing resource shortages. The comparison grew more painful as German tank production faced escalating challenges from Allied strategic bombing campaigns. The bombing targeted key bottlenecks in Panther and Tiger production chains with devastating effectiveness. The Maybach engine plant suffered severe damage during a Royal Air Force raid on April 27, 1944. The attack involved over 300 aircraft and destroyed both engine and gearbox production facilities. Tank engine and transmission manufacturing halted completely for 6 months. When production finally resumed in November 1944, quality control had degraded significantly. Slave labour, increasingly employed in German factories as workers were conscripted for military service, introduced deliberate sabotage. Components were assembled incorrectly, parts were damaged during installation. Quality standards that had already been problematic became catastrophic. These problems never affected Sherman production, safely located in American factories far from combat zones and staffed by motivated workers earning good wages under decent working conditions. The fundamental difference between American and German tank production lay not in engineering knowledge, but in industrial capability and underlying design philosophy. German engineers understood automotive principles as well as their American counterparts, possessing extensive theoretical knowledge and scientific expertise. They simply never applied those principles consistently to tank design, instead prioritizing factors that created impressive specifications but poor reliability in field conditions. German tanks emphasized performance characteristics that looked formidable on paper but demanded complex maintenance procedures by highly trained specialists. The Panther's powerful gun and thick frontal armour came at the cost of an overtaxed powertrain that couldn't reliably support the vehicle's weight. The Tiger's formidable capabilities required constant expert attention and frequent repairs using specialized equipment. These trade-offs might have been acceptable if German industry could produce enough vehicles and spare parts to maintain them. It could not, particularly as material shortages worsened throughout 1944. American engineers trained in automotive mass production through decades of civilian industry experience, designed tanks that could be manufactured by tens of thousands and maintained by mechanics with basic training using skills learned in civilian life. The Sherman powertrain used components proven in commercial service with design principles borrowed directly from automobile and truck manufacturing. Features that seemed like unnecessary luxury to German designers proved invaluable in combat operations. By spring 1944, Wehrmacht units on all fronts reported increasing mechanical problems as manufacturing quality degraded and spare parts became scarce. Panthers required transport by rail for movements exceeding 100 kilometers because their final drives couldn't survive sustained road marches. Field commands issued explicit orders restricting Panther movement to preserve vehicles for actual combat rather than losing them to mechanical failure during approach marches. The recovery vehicle, built on a Panther chassis to recover disabled Panthers, shared the same reliability problems as the tanks it was supposed to rescue. German commanders faced the grim reality where mechanical failures eliminated more tanks than enemy action, with some units reporting that 70% of tank losses resulted from breakdowns rather than combat damage. The irony was devastating. Germany's most technically advanced tanks were being defeated not by superior enemy weapons, but by their own mechanical inadequacy. Meanwhile, Sherman production continued at unprecedented rates that German industry could never match. American factories produced over 49,000 Sherman tanks during the war, more than all German tank production, of all types combined. British Commonwealth forces received thousands through Lend-Lease programs. The Soviet Union received over 4,000 diesel variants. Chinese forces in Burma used Shermans to devastating effect against Japanese armor. Every theatre where Sherman served confirmed what Kummersdorf testing had revealed years earlier. German tank crews who captured and used Shermans universally praised their automotive excellence in letters, reports, and post-war interviews. Reports from the Eastern Front noted that German mechanics found even the most complex Sherman engine variants easier to troubleshoot compared to German tank engines that required specialized knowledge and equipment. The Ford engine, praised by Allied crews for exceptional reliability and power output, seemed remarkably dependable to German mechanics accustomed to engines that required constant adjustment of valve clearances, ignition timing, and carburetor settings. The Sherman's generous design margins provided another advantage that German engineers came to appreciate through bitter experience. The basic transmission and final drive components originally specified for 30-ton vehicles required no major modification to handle heavier assault variants with significantly increased armor protection. The same components that powered standard Shermans successfully handled experimental engines, producing substantially more power without failure or need for reinforcement. German engineers calculated that such overbuilding represented waste, excess capacity that increased production costs and used scarce materials without immediate benefit. American engineers understood that margins provided growth potential for future upgrades and battlefield reliability that made the investment worthwhile over the vehicle's service life. This philosophical difference reflected broader contrasts between German theoretical optimization and American practical engineering approaches. By summer 1944, German tank commanders facing the Allied invasion in Normandy knew their technical disadvantages extended far beyond individual vehicle capabilities. American artillery superiority, devastating close air support, and overwhelming logistical capacity combined to overwhelm German forces regardless of tank specifications or tactical prowess. But the Sherman's reliability meant American armored units could sustain continuous operations that German panzer divisions simply could not match. American tank battalions could launch attacks, sustain combat operations, conduct pursuits, and immediately prepare for the next operation without extensive maintenance halts. German panzer divisions had to carefully husband their limited operational vehicles calculating that every movement consumed precious remaining component life and brought mechanical failure closer. The difference in operational availability determined which force could maintain offensive pressure and which had to ration its limited combat power. German use of captured Shermans in combat operations provided final proof of American automotive superiority from the German perspective. Special operations requiring vehicles to function without breakdowns while operating behind enemy lines far from any support could only rely on American equipment. German tanks, even when fully operational, couldn't guarantee the sustained performance such missions required. The admission was implicit but unmistakable in German planning documents. January 1945 brought the final official acknowledgement of German automotive failure when the Panzer Commission produced reports documenting catastrophic final drive failures across all German tank types. Prior to offensive operations, there were 500 defective final drives in medium tanks, 370 in Panthers, and roughly 100 in Tigers. Additionally, approximately 200 failures had been reported in tank destroyers based on foreign chassis designs. The operational impact was devastating. Orderly utilization of tanks became impossible as troops lost confidence in their vehicles. In some situations, entire tanks were abandoned simply because of final drive problems, with crews fearing they would be stranded and captured. German tanks built to intimidate through impressive technical specifications failed in the most fundamental requirement of armoured vehicles: mechanical reliability sufficient to reach the battlefield and complete assigned missions. As Kummersdorf prepared for evacuation in early 1945, with Soviet forces advancing relentlessly toward Berlin, engineers frantically packed decades of testing data and shipped documentation to facilities farther west. Some of the captured tanks, including at least 2 Shermans, were pressed into improvised service with combat units desperately defending the approaches to the capital. These vehicles would fight alongside German designs in the final desperate battles, providing one last comparison under actual combat conditions that would prove more devastating than any laboratory test. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out. The German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even experienced crews who had grown accustomed to poor reliability. In the chaos of Germany's final collapse, American automotive engineering principles demonstrated their superiority one last time through simple dependability when everything else was falling apart. The story of War Daddy 2 and dozens of other Shermans tested at Kummersdorf represents one of the great industrial disparities of World War II. German engineers working within a system that prioritized theoretical perfection over practical utility produced tanks that looked impressive on paper but failed in sustained field operations. American engineers applying decades of automotive manufacturing experience to military requirements produced tanks that lacked technical sophistication in many areas but worked reliably under conditions that defeated German equipment. In armoured warfare, as in most military operations, the weapon that functions when needed beats the weapon that might be theoretically superior if it could reach the battlefield and complete its mission. This fundamental truth, proven exhaustively through German testing programs, had been staring Wehrmacht leadership in the face since 1943. Yet institutional momentum and political pressure prevented the radical changes needed to address these problems before they became catastrophic. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed years earlier. Systematic examination of destroyed German tanks found mechanical failures as common as combat damage as causes of total loss. Final drives broken from stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded them to the critical importance of reliability and maintainability in sustained combat operations. They built tanks that no conscript mechanic could maintain without extensive specialized training, powered by engines that demanded constant expert attention from skilled technicians, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units across multiple theatres. The complexity that German engineers viewed as sophistication became a liability when multiplied across thousands of vehicles operating under combat conditions far from factory-level maintenance facilities. The lessons learned through testing at Kummersdorf directly influenced German tank design, thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development, abandoning the perfectionist approach that had proven so costly during the war. The resulting Leopard 1 incorporated many design philosophies that had made the Sherman successful throughout World War II. Robust powertrain, with substantial design margins that could handle stress beyond normal operating parameters. Easy maintenance requiring minimal specialized tools and accessible to mechanics with standard automotive training. Standardized components enabling rapid field repairs without factory-level precision equipment. Growth potential allowing future upgrades without complete vehicle redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. Its success validated the American approach that German engineers had discovered too late during their exhaustive testing programs. Practical engineering focused on reliability and maintainability proved far more valuable than theoretical optimization that couldn't be sustained under real-world operating conditions. The captured Shermans at Kummersdorf, including War Daddy 2, with its distinctive name still painted on the hull, represented far more than enemy equipment brought home for technical examination. They were tangible proof that industrial maturity and sound engineering principles, based on practical experience, mattered more than theoretical technical innovation, pursued without regard to manufacturing reality or operational requirements. German tank designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority through qualitative superiority. They were fundamentally wrong about this assumption. American tank designers built reliable vehicles because they understood through hard industrial experience that logistics, maintenance capability, and sustained operational availability determined victory in modern mechanized warfare. They were absolutely right, and their approach proved decisive across every theatre where armoured forces engaged. The reliability gap between Sherman and German tanks influenced not just tactical armoured warfare, but fundamentally shaped broader understanding of military industrial capacity and its decisive role in modern conflict. Germany entered World War II with technical advantages in many weapons systems, possessing scientific knowledge and engineering expertise that exceeded most opponents in specific areas. However, Germany lacks the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production, while simultaneously fighting enemies on multiple fronts. The United States entered the war with weapons that were less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities, while continuously improving quality, reliability, and performance based on combat feedback from multiple theatres. This industrial approach, perfect lead production, proved far more effective than German exemplified by Sherman tank design and technical sophistication applied to small-scale production, with inadequate attention to practical operational requirements. The mathematics was simple and brutally clear when examined objectively through the lens of Kummersdorf testing data. A Sherman with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy or required 3 days of maintenance for every day of operations. A tank battalion, with 80% of its vehicles operational, could execute missions that a battalion with 40% operational vehicles simply could not attempt under any circumstances. Reliability wasn't just a convenience factor or secondary consideration in armoured warfare. It was the foundation of operational effectiveness, determining whether armoured units could execute their assigned missions when called upon. German tanks consistently failed this fundamental test throughout the war, despite impressive specifications and theoretical capabilities. American tanks consistently passed it through sound engineering and manufacturing practices developed over decades of civilian automotive experience. Kummersdorf testing had proven this beyond any reasonable doubt by mid-1943, even as German commanders continued deploying Panthers and Tigers that looked fearsome and possessed impressive specifications but couldn't be relied upon to function when needed most. The disconnect between testing results and operational decisions reflected institutional problems within German military leadership that extended far beyond engineering or manufacturing limitations. The Sherman tank didn't defeat German armour through superior firepower or thicker steel. It won through something far more devastating: the crushing realization that American industrial philosophy had rendered German engineering excellence irrelevant. Every test at Kummersdorf proved that reliability trumped sophistication, that mass production defeated perfectionism, and that a tank which simply worked was worth more than 10 that broke down before reaching battle. War Daddy 2 had delivered the most brutal lesson of the war. Germany wasn't losing because their tanks weren't good enough on paper. They were losing because American tanks actually functioned when it mattered most.